next identity that we need to be able to prove is that the inverse cos of negative x is equal to pi minus the inverse cos of x. Now, this one looks a little bit different from the last two, and that's because y equals sine x and tan x are odd functions, whereas y equals cos x is an even function. Now, remember what that means. It means that if we were to fold it on the y-axis, it would have that perfect symmetry left to right. And so that makes quite a different situation than the other two, which had odd symmetry, where we can take one section of the curve, like y equals tan x, and basically spin it like blades of a fan around the origin, and it would sit on top of itself again. So to start this one, start it the exact same way as you did before with the last two. Take the left-hand side and just let it equal theta. So let's write let the left-hand side equal theta, therefore theta equals the inverse cos of negative x. Okay, we've started each one that way, so it's nice to have a little bit of continuity and keep going the same way. What did we do next? Well, we rearranged that, didn't we? We said that means that the cos of theta is equal to negative x. All right, so far, same process. What did we do next? Then we rearranged this to say x must be negative cos theta, and of course you can write those round either way. So all I've done there is multiply or divide both sides by -1. So now I've got it in terms of what this x actually is. Okay, now at this point we need to go over here and have a think about our graph. Now the reason I'm going to do that is I want to change this minus cos theta into something else. So thinking about what I know about cos theta and therefore about minus cos theta, I can come up with some other statements here that might be, other expressions that are equal to this one but look different. And I'm sort of looking for something that might have pi minus something in it, because this is my finish line. Now, what would happen if I graphed y equals negative cos theta? Let's imagine that this is not cos of x, but cos of theta. What would y equals negative cos theta look like? Yeah, it would be the upside down version, wouldn't it? So if I tipped this one upside down, in other words, well, that's a bit wonky. In other words, replaced y with negative y, this red one could be called y equals negative cos theta, couldn't it? Now, why have I gone for that? Well, I've got negative cos theta here, so it sort of makes sense to graph y equals that, and then I can think what other graphs might also look like this red one. Now, is there any other way that I could generate the red graph from the black one without flipping it upside down? What else could I do that would amount to the same thing? Well, I could slide it, couldn't I? Couldn't I slide this black one to the left or to the right and it would sit perfectly on top of the red one? I think I could. How far would I need to slide it? Half the period. So if the period is 2 pi for this curve, then if I slid it just pi either way, or 180 degrees either way, it would sit on top of the red one. So in other words, this red curve here could also be called y equals cos of not theta, but theta plus pi. If I've slid it pi units to the left, I could also call it y equals cos theta minus pi if I slid it pi units to the right, because we can see that going left or right pi units is going to amount to the same thing. Is there anything else I could call it? Well, have a look at the evenness of both of these curves. If I take the cos of, say, 30 degrees, just working in degrees again so you're comfortable, and the cos of negative 30 degrees, I get the exact same y value, don't I? The same answer. So in other words, looking at this one here, where I'm doing theta minus pi, if I did pi minus theta and then took the cos of that, would I get the same thing? Well, let's think through. With any two numbers that you're subtracting, let's think of easy numbers like 5 minus 3, it's 2. 3 minus 5, it's minus 2. If I take the cos of a number or its negative counterpart, won't I get the exact same thing anyway because of the evenness of the curve? I will. So that means that this one is exactly the same graph as this one. And I've done them all in red here to show that this guy and these ones, they're the exact same curve. Because whether I tip the black one upside down to generate its formula, or I slide it along pi units, and this one is the same as that one, they're all the same thing. So what I'm doing this for, really, where am I going with this? I'm trying to make another expression for x. I can see that if negative cos of x, cos of theta, and cos of pi minus theta are effectively the same thing, because they're the same graph, then if x is equal to this, then x must also be equal to that. So now I can sub that in like that. Okay, where are we going now? Well, we're trying to get inverse cos, not cos. So it makes sense that our next step now is to rewrite this and say that the inverse cos of x is equal to pi minus theta. Okay, now we're nearly there. The way you decide to finish off is up to you. There's lots of ways that you could end up proving this. Remember the way we started? We said let's let the left-hand side equal theta. So this whole thing was equal to theta here. All right, so what we're really trying to show is that the right-hand side is also theta. So at this point I could say right-hand side is equal to, let's just write out what we were given, pi minus inverse cos of x. But we've just shown that the inverse cos of x is this. So surely we can sub this in here for inverse cos of x, minus pi minus theta. And now expanding our brackets, we've got pi minus pi plus theta, which is just theta. And that is equal to the left-hand side because in the beginning we defined our left-hand side as that. So there's a few different ways of setting out the end part. Really the trickiest bit was going from here to here, working out that that is the same as that. Now there's lots of ways that you could prove that. You could even write a sentence that says next to this, because flipping y equals cos theta upside down to create y equals negative cos theta is the same as taking the cos of negative theta, or theta for that matter, and adding or subtracting pi to it. So that can confirm that these two are the same. You can even draw the graphs and label it as this, and also label it as that, and write next to that same thing. Anything that you write or draw or explain in a proof is a reason, and there's so many ways of doing that. You can write a sentence, you can draw pictures, you can label them with arrows, as long as it's really clear how you knew that this was equal to this. And over here, I think you can see from my working that I've identified how I know that they're the same. In fact, how do I know that these two are the same? We discussed it, but we didn't write it down. We could write same because it's an even function. So you'd literally write in here because y equals cos of theta is even. And now I've really covered it. Okay, the fourth and final identity that we need to be able to prove is this one. Now this one is basically, in a nutshell, the same thing as this, and we've already learnt this identity before. It's really quite an obvious one if you consider that in a right angle triangle, we've got already 90 degrees. So these two angles have to add to 90. So whatever this one is, this one will be 90 minus that. So if this is 20, this would be 70. If this is 40, this would be 50, and so on. And we've also seen that the sine of this angle is equal to the cosine of this angle, and vice versa. So, for example, the sine of 20 would be the same as the cos of 70. And we've already seen that the sine and the cos of 45 are exactly the same. So this rings true all the way through, and it's something that we've already learnt. So how are we going to use it? Well, basically here we're just saying this is an angle, and this is another angle, and they both add up to 90 degrees. Now here this is in radians, so let's go to this little identity here and change it also to radians so that we're thinking in radians a little more now. Okay, so this is something that we should be comfortable with. These two angles add up to 90. Obviously, they must be like this. So to prove it algebraically, all we need to do is just let one of these parts equal a pronumeral. Let's say we'll let theta equal the inverse sine of x. So now this whole part here is theta. Now we can rearrange this and say that means that the sine of theta is equal to x. Okay. Now if the sine of theta is equal to x, have a look up here. We know that the sine of theta is equal to the cos of 90 degrees, or pi on 2, minus theta. So herefore we can say, therefore, x is going to be equal to not just sine theta, but the cos of pi on 2 minus theta. So we've literally just used this identity, and you can start your proof by writing that one down if you want to. Even using the little triangle is not silly. It reminds you where you're going and what you're doing. Okay, now what are we doing? We've just said we've found an expression here for x. Now can we make that in terms of inverse cos x? Yep, we can write inverse cos of x is now equal to pi minus 2 minus theta. Now, when we started, we said let's let theta equal this. All right, so let's go back a step then and say, therefore, the left-hand side is equal to inverse sine of x plus inverse cos of x. And that is equal to, well, we've let inverse sine of x equal theta. We've already stated that earlier, so that's theta. And inverse cos of x, we've said here, it's plus pi over 2 minus theta. And both of those simplify out to give you pi on 2. So the left-hand side equals pi on 2, and the right-hand side also clearly equals pi on 2. So that's our proof, and we're actually finished. This one's probably a little more straightforward. You've just got to think what you're doing. You're letting one thing equal theta, rearranging it, then you're using this identity, and then rearranging that, and then stating that the left-hand side simplifies out to the right-hand side.